All right, so now that we have described how we can represent stress inside of a fluid, and we can derive now finally the momentum equation at the differential level. And so we start from what we have derived to that point. So we derived for an incompressible flow a statement of mass conservation at the differential level, which is the continuity equation, or the incompressibility condition. Divergence of u is equal to 0. And for any continuum, we've discussed that we can write at the differential level. We can write Newton's second law as the material derivative of the velocity field with respect to time is equal to the divergence of the tensor, of the stress tensor, plus the body forces. Remember, this term here represents the acceleration of a material element. This term here represents the integral of the surface forces on the control surface, and this represents the integral of the body forces inside of the control volume. Right, so those two terms together represent the resultant forces, so all of the external forces applied onto a material element. So the only thing we have to do to find our momentum equation is to compute what is the divergence of the stress tensor given the expression for the stress tensor that we have in our Newtonian fluid. So what is the divergence of minus the pressure field times the identity plus our other tensor, which is k minus 2/3 of mu times the divergence of u times the identity matrix plus 2 mu times the rate of strain tensor. Actually, before we compute this divergence, let me just make this quick statement here. So this is our stress tensor inside of our Newtonian fluid, right? But remember that in our case, we are interested in incompressible flows, right? We only, in IFD, we only look at incompressible flows. And for incompressible flows, the divergence of u is equal to 0, and therefore this term here is equal to 0. So you see that actually for incompressible flows, we don't need to determine the bulk viscosity of the fluid. It's not a relevant material property because it doesn't come into a constitutive relationship. One thing which is important to note then is that really the bulk viscosity here only comes into the constitutive relationship when the divergence of u is non-equal to 0. And remember that a divergence of u, if it's non-equal to 0, this divergence of u represents how a material element expands or how a material element compresses if this divergence field is negative. So when divergence is positive, for instance, think about this represents really an expanding control volume, and so the bulk viscosity here is really related to compression and extension of material elements. And so, for instance, this bulk viscosity here can come into play if you're thinking about the propagation of sound waves, because sound waves are waves where air or the fluid is being compressed. But for an incompressible flow, we will never really see the effect of bulk viscosity. So in IFD, we focus on incompressible flows for which the divergence of u is equal to 0, and therefore, for the remainder of this class, really, our stress tensor we can always write as minus a pressure times the identity plus 2 mu times the rate of strain tensor. This is the form of the stress tensor that we will always use in this class, okay? And so we can compute the divergence of T. What is the divergence of T for our Newtonian fluid? So it is going to be equal to minus times the divergence of Pi plus 2 mu times the divergence of E. Now I will spare you the details, but this here is equal to the gradient of, so this equals to the gradient of P. And after you've done the calculation, the divergence of E is actually equal to the Laplacian of U. So finally, we can write our Navier-Stokes equations for an incompressible flow. Mass conservation takes the form of the continuity equation, which for an incompressible flow reduces to the incompressibility condition, divergence of U is equal to 0. And the momentum equation we can write as rho times the material derivative of U, which in Cartesian coordinate I will write as partial U partial T plus U grad U equal to, here, minus the gradient of P plus the dynamic viscosity, times the Laplacian of U plus body forces F. And this here is the momentum equation. All right, so we finally finished our derivation of the Navier-Stokes equation. All right, so because here we have a lot of nabla and you may not be able to really see what these equations look like in reality, here is how you will write them in Cartesian coordinate. Here they are. So this equation here, so you have really 4 equations, 4 unknowns. Your unknowns are U, V, and W, V, W, and P. And you have those 4 scalar equations. This equation here is the continuity equation. And these 3 equations are the vector, are the components of the vector equality which correspond to the momentum equation. And this here, which is the material, the rho times the material derivative of the velocity, represents the acceleration of a material element, or the change of momentum of a material element. And these 2 forces, these 2 terms here, well, hold on. This here represents the pressure. This here represents the viscous force. One way to think about the viscous forces is that viscous forces is the part of the stress tensor which is linear or which depends on the deformation, right? And pressure here is really the isotropic stress which arises inside of a fluid which you're trying to compress, right? So you don't need necessarily deformation for pressure to arise. We saw that when we looked at the stress developing in the fluid when it's in static equilibrium, so when there is no deformation. But pressure really arises inside of a fluid if the kinematics of the flow tends to induce a compression. And if a material element is, because of the flow around, it tends to be compressed, or because a material element is being pushed against a wall, for instance, then the pressure will increase. So this is the pressure. Those 2 terms together, they represent the surface forces, so the sum, the integral on the control surface of the surface forces on our material element, on a small material element. And finally, this last term here represent the body forces, so that would represent the volume integral on a differential control volume of the body forces.